All right, so up next is Kshitijaa, almost correctly pronounced. And yeah, she likes to use AI, machine learning, and networks to optimize complex systems and make them faster and easier to understand. And the talk will introduce us to several methods to analyze real-world problems by using graph-based network solutions. So yeah, in a more connected world where everything is kind of networked with each other, this sounds like a thing you want to know about. So yes, please welcome her with an applause. Thank you.
Good evening, everyone, and thank you for sticking around for the last talk of this conference. I will start by asking one question, if my cursor goes there. What is a network? Does anyone want to give it a shot? We're not talking about neural networks, by the way, the other types of networks. Yes. Yes, so you mean a graph. Okay. Anyone else? Oh, yeah, sorry, you were saying more? Or no? Okay, cool, yeah. Okay, so this are multiple entities that can communicate with each other. I think the definition I will go with is a mix of both. That one seems very mathy, this one seems very applied, and it's everything. In the words of the professor who introduced me to networks in the first place, Professor Ulrich Brandes, network is not a graph, it's data on a diet. Diet itself is a pun that you'll understand in the next slide. So networks are data on diets. If you just Google the definition of diet, it is something that consists of two elements or parts, as you also mentioned. In the context of networks specifically, we have nodes and edges. The pink and blue thing is a node, and the line connecting them is an edge. An edge can be undirected, directed. It can be a mix of both. Both can be undirected. We have combinations. But the term edge can also be changed with link, dyad, so on and so forth. But where is the data when we say it's data on diodes? It can be in the whole graph. In this case, our graph consists entirely of two nodes and one edge. It can be on the edge or it can be on the nodes. These are places to put data. Now, extending from our definition of diode, what do you think this triangle might be called? Triad. Yes, perfect. It is a triad. What's this? Slightly difficult question. Triangle, okay. Broken triangle or broken triad? Okay. Could you repeat that? Spanning tree. Oh, okay. We're going in that territory. We can just call it an open triad. We go with simple answers usually, but it has another term called a forbidden triad. Any guesses why it might be forbidden? Okay, anyways, I will come to why it's forbidden in this case. There was this paper called The Strength of Weak Ties, very, very old, because like seeing how fast everything is evolving, it's kind of ancient at this point, from 1973. In a sociology journal, not really computer science or anything. I don't know if Python was a thing back then. This is called forbidden triad because it is very, very rare to observe these kind of open triads in a real world. In this case, edges AB and AC are what we call as strong ties. It could be friendships, for example. If you're a good friend with someone, we can call it a strong tie. And this weak tie, you'll observe that it automatically forms when there are two strong ties connected like that. To give some more context in the real world example, if you look at this picture, assume you're the blue person there, and you have your own circle of strong ties. And these people will have their own circle, which is outside your strong tie, but it's their strong tie. And you kind of develop this weak tie to those 2-degree connections. Even though these are multiple independent groups happening everywhere, you kind of have a connection to all of them. But why am I talking about all of this suddenly in a Python conference of all places? Another paper. For context, I'm a PhD student, so you'll have many papers. There's this paper called The Role of Social Networks in Information Diffusion. which was authored by many people from Facebook. So they had access to all the data, or a lot of data. And this is the graph of Facebook users and how they connect with each other. If a thing is brighter, like if a point is brighter, it means there are more people. And blue lines are the edges connecting all of them. And do you want to guess how many monthly active users Facebook has? Any guesses in the world? Sorry? 2 billion. Okay. Anyone else? 20 billion. Okay. Are they all bots? Have you heard of that experiment where if you ask many people to guess how many candies are there in a bowl, the average tends to be closer to the answer? We can try something similar here. So we have 2 billion, 20 billion, 400. Okay. I think that experiment will not work out here. But the answer is 3 billion. So I think you were pretty close. Yay. And in this paper, they found out that the influence these strong ties and weak ties have on your feed are pretty different. If you look at this plot, you have comments, messages, photos, and threads. Threads are like when you have a conversation within post comment section, things like that. And they found out that weak ties actually have a lot of way more influence than your strong ties do. And it's not entirely counterintuitive. Like the first thing itself is that you have way more weak ties than you have strong ties. Well, that was slightly surprising. But there was yet another study on a different social media now, LinkedIn, which I'm assuming more people might be more active on. I don't have the number of monthly active users there, but still, okay, have a logo. So LinkedIn, some people at LinkedIn, again, they had access to a lot of data. They conducted this very large-scale experiment on their users. You say yes to all of those things in terms and conditions, probably. And I don't know if the users were aware of it, but anyways, there's this thing on LinkedIn called People You May Know page, where they recommend people you can connect to based on some common criteria, or if you know someone, they know someone, kind of like that, with mutual connections and so on and so forth. And to put into perspective the scale of this experiment, there was a network of 20 million people over a 5-year period, and there were 2 billion new ties that were created in that period, and people applied to 600,000 new jobs. So there was a lot of data going on. And over here, they tried to operationalize how well connected people are based on 2 factors. The first one was amount of interactions, or like how many messages people are exchanging with each other. And the second one was the number of mutual connections. And in this case, this is a figure from the paper. What they did was they had 2 groups of people. For one of them, they would recommend mainly the strong ties. For the other one, they would recommend only the weak ties. So if you can see here, the red dot is a strong tie. So for that person, if we look at this area, we'll see that they were recommended more of strong ties kind of things. And the blue one were recommended weak ties in their People You May Know page. And after this, they found out that weak ties were actually more helpful in finding a job. So again, going back to that paper about strength of weak ties, they do already establish that weak tie is important. But in this case, it was the first control study and a large-scale study where you could see how things are happening. But there were also some caveats to it. For example, they found out that the strength of weak ties is not really linear. So we would assume that the weaker the tie is, the stronger it is, but in real world, that kind of doesn't make sense. In this experiment, they found out that it follows a U-shape. So if you start from the weakest, if you have 2 extremes, weakest and strongest, weakest is also not very helpful, strongest is not really helpful. It kind of goes like that. So there's like this sweet spot. And they found out that the sweet spot lies at when you have 10 mutual connections for their data set. But it depends a lot on the person. If you connect with everyone, I think it won't be 10. If you connect with very less people, it might be less than 10. But anyways, the point was, there's this sweet spot of your weak tie to strong tie, where it's most helpful to know the person in a very capitalistic society-ish way. And it also makes intuitive sense. because people who are very close to you will also have very similar social circles. So there is less scope of finding something new. And people who are slightly away, the more away they are, the more different your social circle might be, and the more different job opportunities they might know of as compared to your circle. But as you keep moving away more and more and more, it just becomes completely different, and it doesn't really remain effective anymore. So that was one finding they suggested. And they also realized that it depends a lot on the context. The strength of weak ties paper, it kind of generalizes that, okay, weak ties are important and they're very strong. They have a lot of strength, not strong. But this paper, they found out that in digital circles, or like more digital occupations like computer science, data science, for example, the moderately weak ties are the most important. But in case of non-digital circles like medicine, for example, which are not as tech heavy, in my opinion, you would see that it's still the strong ties that make more sense. So yeah, that was my TLDR about this paper. And all it says is LinkedIn can be good, or like these kind of social networks are very helpful in achieving certain things if you kind of strategize them a bit. But now coming to the real world networks, I have a corporate network as well. It's called Crackhart's corporate network, and Crackhart is a professor who did a lot of network science. So consider the following situation. There's this company called Halifax. Names are changed to preserve anonymity. This is what they call them in the paper as well. They're a large defense contractor on US's West Coast, and they have this small team of people who belong to the aircraft engine manufacturing division's internal auditing staff. And since some time, they've been having problems with the numbers of like the tasks that they're doing. So in this case, suppose they're supposed, imagine they're supposed to complete 10 reports per month, or like 10 audits per month, but they're doing 7 or 8. So there is a lot of backlog going on. And to add to the problems, their manager also decides to leave the company. In the past, how they replaced was just by trying to promote someone who is from the same team, because they already know how the team dynamics work, and they don't really need to be trained for many things, and so on and so forth. But in this case, they decide to bring in someone else. And the someone else was Manuel. Manuel belonged to some other team of the same company, and he had no idea what things are going on here, but he knew that there were problems. And the team members themselves were not really aware of those problems in the first place. So Manuel decides to try some restructuring. And in this case, the restructuring was proposing another team dynamic situation. So how things work till now is that we have the yellow nodes, which are secretaries, and we have these green nodes that are auditors. And how it works was that the green nodes will go to clients or customers or companies, and they see how the things are there, like kind of doing client visits. They bring back a lot of paperwork, and we have the auditing team who helps them. And the main problem is there was a lack of coordination between these auditors and the secretaries. So Manuel, he decides that what if we just assign one secretary per person? So like a secretary just has a bunch of auditors who are connected to them. And whenever these auditors need a secretary, they go to that one person. On paper, this seemed to work. The numbers were improving. But at the same time, within that team, there were many conflicts arising. And there were complaints everywhere. And Manuel just joined the team, so it's not good for him if things are not really working well. Now, what does he do? He meets Professor David Crackhart, the person who also authored this paper. And Professor Crackhart decides to ask 2 questions from all of these people. The first one was, who among the other 13 people in the auditing group do you typically go for help or advice when you encounter a problem? And the second was, who typically comes to you for help or advice? So these are like 2 directions. Who do you go to, and who comes to you? With these 2 questions, he wanted to see how the interpersonal relationships are really working there, or what is the influence that is happening within the network. With those questions, he created this network, where we see the structure is slightly similar. Like the green nodes are going to their managers, for example, the yellow ones as well. But we see that Nancy is up here. There are managers who are also going to Nancy for help. And Manuel is also going to Nancy for help. Nancy goes to Donna, but that's mainly it. So what do you think was the conclusion from this, the survey and the network? What do you think Manuel should do? Should he make Nancy the new manager? Okay. He decides to talk to Nancy, which is wonderful because communication is important. And then they talk and talk and talk. They talk for 2 months, I think, if I remember correctly. And they arrive on a solution. So Nancy knew her team the best, and her team also trusted her. So her input was especially important. It doesn't seem feasible to go to every team post and ask them things unless it's a very do or die situation. So this was a good sweet spot. And with Nancy, they figured out that instead of going with manual solution, we tried to find a middle ground. Instead of assigning secretaries to auditors, like just one-on-one thing where they don't really have any autonomy or any choice in the projects that they're taking, they have a nicer solution where they temporarily assign secretaries for those specific audits, and secretaries also have a say on what really they work on. So again, a sweet spot, but it worked out because of that one survey from where you kind of created this network-ish thing. So in this case, the network is very different from the network we saw before of like Facebook or LinkedIn, where it's very obvious to see what the edges and nodes represent. In this case, it was just one survey, but we could use it in a pictorial form to see how dependencies work in that one corporate structure. Okay, now another network. But before that, there's a small theory, some very, very small theory. We have this structure called core-periphery. It is pretty simple to understand. We have a core where every node is connected to each other, and we have a periphery where the nodes are only and only connected to the core. This is an ideal core-periphery structure. And it's observed a lot in the wild. Not exactly, but to some extent. We have another paper. This one is about monkeys from 1987. We have this dude called Edward, and we have this other female monkey. They didn't name her. I'm sad. But they discovered this network based on certain interactions. Do you want to guess what might have been the methodology behind creating this network? Food? So you mean giving food to each other, kind of like that? Okay. I don't know how selfish monkeys are. Okay. That's a good idea. Cool food. Yeah. Sorry? Grooming? Yeah, that's also a wonderful idea. I know there are cow grooming networks, but this one is not grooming, sadly. Any other? Sorry? Hitting each other. Oh. Fighting network. Okay. Good idea, but not really. Okay. In this case, in that forest where the data was collected, there was a small pond. And whenever two monkeys were at the pond at the same time, the strength of the edge between them increased by 1 unit. So if two monkeys are there very often, they'll have a stronger edge between them. It kind of signaled that monkeys who are closely bound or who are often hang out together, they will probably go to the pond at the same time. And over here, the black structure in the middle, that is our core, like when you try to fit the core-periphery model on this. And the gray edges over here, they're the periphery. But at the same time, we also have these dotted lines. These are the edges that don't necessarily fit the core-periphery structure, but they exist. So the solid lines are the ones which do fit our model, and dotted ones are that don't. Real-world data fits the models to some extent, but there's always some exceptions going on. And what they found out was that they have this group of, I think, mainly very strong mothers, so like hats off to them, who were often part of this core, and they also had their kids and everything going on. But when they want to see how a whole group looks like, they can focus on the core, and from there they can also find the periphery of how things are going on. Apart from monkeys, we also see this structure in trade networks. There was this paper called The WTO Promotes Trades Strongly but Evenly in 2007. And they figured out that the trade networks also follow core-periphery structure to some extent. We have these countries in the middle, which form the core, and we have some on the periphery, which form the periphery, or which are mainly connected to the core. Again, they try to fit this model, this data to our core-periphery model, and they found out that it fits pretty nicely. If you look at the stats over here, there were 16 edges missing in the core and 23 missing in the periphery, which amounts to only 2.3% edges being added or removed. So, well, even though it wasn't very expected because the world is supposed to be, the trade is supposed to be free and everywhere and so on and so forth, but that wasn't happening as evenly as one would want. Now, after trade networks, we have another different type of network. This is the last example, so there won't be more. Again, a paper from 1979 about the river trade network of Russia. And the question they want to answer is, could we have known that Moscow will become the Russian capital today? Were there any signals that might have informed us? To give some context, these are the rivers in Russia. And the dots you see, or the square thingy you see, those are certain cities or certain ports. And if we want to see it in a network form, this is what it looks like, or in a graph form. Over here, we want to look at two values. The first one is to say if there was a ship going between two cities, what are the chances that it'll stop at a city C in the middle? You want to see the intermediate node occurrence. On any path between two cities, what all cities are lying in the middle? And the second thing we want to see is aggregate distance of each short path. So if I have a city ABC something, how far is each city from me if I just follow the shortest path? So for example, here, if I look at this particular place, Volgar, I can't see. Anyways, it's over there. The shortest path to every other city will probably not the smallest value. As compared if you see something in this region, for example, you'll find out that the shortest paths, the sum of shortest paths, is actually a smaller value. And when I say intermediate node occurrence rate, if you have paths from between every two pairs of cities, how many times is your city or your city ABC falling on that path? To operationalize it, okay, by the way, this is Moscow. I didn't say that. So to operationalize it, we look at, what these two values signify is low travel distance, because if you have a shortest path to all the other cities, it means anyone can easily reach your city. And frequent stopovers. If people are going somewhere else and they're stopping at your city, it's also good for you, because they will buy things there, they might have some random side trades going on, and so on and so forth. And we just look at these two values in this particular graph. We have percentage of intermediate node occurrence rate, again, like the stopovers. And we have the aggregate shortest path distance. We want this value to be less because the city should be closer to everything else. And we want this value to be high. There should be more stopovers. And we saw that Moscow lies on a pretty extreme end when we plot this graph, which was interesting. This might not be the only reason, but what it tells us is through these seemingly random things, if we try to look into detail, we can find some signals that can inform us about what's going to happen. Again, this is not the only factor. There will be so many other things like geopolitics and so on and so forth, but signs are everywhere. And if we want to look at the network theory terms, we call the low travel distance betweenness centrality and frequent stopovers closeness centrality. Centrality is just a way of saying how important a node is in the given context. So stopover is a context. That is how we are trying to calculate the centrality in this case. And if we go back to our corporate network, we can call the height from top. So in this case, they try to arrange this network in a way that most arrows are pointing upwards. So because they want to rank it. And in this case, the rank can be called influence centrality because Nancy seems to have the most influence, followed by how many people are there in that ranking. And yeah, so that was the end of my talk. And we saw many, many things of like what is a network, forbidden triad, Facebook, LinkedIn, monkey network, trade network, Moscow, so on and so forth. The point of this talk was to tell how networks hold a lot of power and seemingly weird data that we might not think of as network type data can be converted to a network and looked at in a different way. Especially in data science, it can be very helpful. Like, for example, if you have 10 guests at an event and 3 of them don't want to sit with each other, you can also create a network out of it and deal with something called a graph coloring problem, where color represents the table they sit at, and you just try to give them a different color. So yeah, that was the summary of this talk. And a big thank you to everyone, especially Professor Ulrich, who introduced me to the world of networks. And please let me know if you have any questions.
We have a few minutes for questions, so raise your hand. If you have any questions? So, oh, I see a raised hand over there.
Thank you for the talk. I wanted to ask, maybe I didn't catch this. I was writing the notes and everything. The monkey network.
Yeah.
You said that the strong connections were the ties between the monkeys who come to the pond together to drink water. No, drink water. Was that?
So okay, let me go back to this slide. Yes, this one. In this case, you weren't really talking about the strong or weak connections. You were just talking about any connection in that case. So,
Okay.
and we want to fit it to the core-periphery structure, that you have a core where everything is connected to everyone, and you have a periphery where they're only connected to the core. So we're just trying to fit that model into this. And dotted lines are the ones that are not fitting in the model. Does that make sense?
Okay. So yeah, I wanted to ask. I didn't catch the conclusion. I thought that it was something that they concluded after they draw the network, but it wasn't that.
So the conclusion was that there is a core. If you just look at the random in the wild, it will feel like, okay, we have monkeys who are connected to each other and there are like some groups. But what they found out was that there is this big group that holds a lot of power in a way. And then there are others who are connected to this small group or to this small core in some way or the other. Yeah. Just about that one core.
Are there more questions in the audience? Yeah, over there.
Thank you so much. What is your preferred pipeline to analyze graphs in Python?
So if you're just starting with graphs, NetworkX is pretty good. They have nice documentation, nice API, and there's a lot of support available, but it is very, very, very slow. So what I often use, like after NetworkX, is NetworkKit, which is a wrapper around a CPP implementation. And over there, everything just works very nicely. The API is not the best. It takes some time to get used to it. The documentation is okay, but they're open source, so you can also always contribute. And they're extremely fast, so that's my preference.
And with the proliferation of all the graph databases, do you have anything, are you using them, or are you like Neo4j or Target Graph and all that?
That is something that I'm starting now. I haven't checked them yet, but Neo4j is the one that, based on what I read, seems to be the best choice to start out with, at least. And I have like 1 or 2 projects that use graph database, but I can tell you after I use them. Yeah.
Thank you.
All right. There one more question. Timon seems to have one.
If you have time, at your first or second slide, you had this tweet about why a network is not a graph, and I still don't understand it.
Sorry?
I still don't understand what is the difference between a network and a graph, if it's composed both on nodes and edges.
Okay, so networks can be of many, many different types, and data also. Okay, so the main difference between network and graph, based on what I also understand from this tweet, is that you can have node attributes and edge attributes that follow completely different formats. So in case of graph, you're mainly looking at that structure, but with networks, you're also looking at those attributes, which can be, like, for example, on Twitter, what does a person talk about? So like the topics associated with them. So it's along with that data on the graph that gives us a network.
Okay,
Yeah.
thank you very much.
You have another question?
A follow-up question, could you also maybe define it the way that you say networks are just domain-specific graphs? Because you were talking about so many different domains, and I kind of like, it's kind of
You mean
like you
domains?
say let's say a graph is the mathematical construct, and the network is a real world application like put onto this mathematical construct. So energy networks or something like that.
So you mean
Just as a definition.
I think across disciplines as well, you follow pretty much the same fundamentals of networks. Like, for example, electric networks or flow networks and for water pipelines, for example, influence networks on Twitter. Most of them have their foundations in physics, and you just extend them and tweak small things, and they do happen to work. And for example, the core-periphery network, which we talked about here, we saw it in monkeys and also in world trade. So the foundations are the same, it's just that terminology can be a bit different. But I wouldn't necessarily say that they're very domain-specific.
Okay, thank you.
All right. I think our time is over. So any questions you may still have, you can ask her in the upper row that will be after the lightning talk. So yeah, thank you very much for your talk.
Thank you.